Hello, a great welcome to the series on Abaqus. Myself Jarajan P. This is tutorial number 10 and provides the analysis of a lug-pin assembly. So let us first go through the problem statement. So as shown here, the lug-pin assembly consists of three lugs that are connected by a single bolt. The geometry of a single lug is shown here. It essentially consists of a rectangular part of 150 by 100 mm dimension, and on the right side it has a semicircular portion of 50 mm radius. A hole is provided under each lug to accommodate the pin, which is of 24 mm diameter. And as shown here, the two ends of the lugs, that is the end lugs, are fixed, and a uniform pressure is applied to the intermediate lug, and this pressure is of 75 MPa. And the lug pin assembly essentially consists of two materials, and the pin will be made up of steel with a E is equal to 2.1 into 10 raised to 5 MPa and a Poisson's ratio of 0.3, and has a yield stress of 640 MPa and an ultimate stress of 800 MPa, and the PLAXIS strain will be taken as a 0.08, that's 8%. And the lug part of the assembly, it is made up of the aluminum with E equal to 7 into 10 raised to 4 MPa and Poisson's ratio of 0.3, and the Fy will be 125 and Fu will be 250, and the PLAXIS strain will be 0.15. So essentially we are proceeding for an elastoplastic analysis, and the pin assembly, the geometry is shown here. It has got a head diameter of 40 mm and a head thickness of 15 mm, and the shank dia is 24 mm, and the hole dia will be 26 mm. So a three-dimensional view of the meshed lug pin assembly is shown here. So to improve the visibility of this tutorial, it is divided into two parts, part A and part B. Part A will cover the modules such as parts, property, assembly, and step, whereas the part B will cover the modules interaction, load, mesh, job, and finally we will review the results through the visualization module. So let us visit the Abaqus. So as already explained, the assembly consists of two parts. One is the lug and the other one is a pin. So let us proceed for creating the lug. So create a new part, call it as lug, and it will be 3D deformable solid extrusion. We keep this as approximately, say for example, say 300 mm. Continue. So it has two parts. So let us first draw the rectangular part, and it has a dimension of 150 by 100. So this is my 150, and this would be 100 mm. So now at the end we have a semicircular part. Let us create it, which is of radius 50 mm. So shall go for creating with using the 2 points. So pick a center point. So this is my center point of the circle. So let us have the starting point, this one, and the end point is this. So now we need to create a circle that represents the hole, which is of essentially 13 mm diameter, 13 mm radius. So draw a circle, the center point over here, and let us keep its radius as 13 mm. 13 mm. Okay, so this means that our sketching is complete, but we are finding one line over here that represents one side which is not required for the model. Let us delete that part. So we have deleted this. Done. Okay, fine. So sketching is over. Let us go for extrusion. Done. And we know that the thickness of the plate is 16 mm. So it's 16 mm. So that's okay for us. So now you find that yes, our part is ready. So just like any other tutorial, it is better that we start partitioning the any part model so that the meshing and all other subsequent operations will be easier for us. So let us first proceed for partitioning this at some critical locations. So this is my XY view. So first, let us divide this into 4 segments, all along the diametrical axis, passing through this center. So we should proceed for partition. Okay, so and we'll use the point and the normal approach. So my horizontal partition should go through this point, okay, and it should be normal to this. So create partition. So we have created a horizontal partition. In a similar way, proceed for creating a vertical partition. So let us select the cells. So done. So we should pass through the center point, okay, and obviously should be normal to this point. This line. Okay, so create partition. So you find that yes, we have divided this lug assembly into 4 parts. 1, 2, 3, 4 parts. Okay, so let us also create a partition at 50 mm from this center, and in fact that edge will correspond to the extreme edge of the second lug. So let us proceed for creating the partition. So we shall use the face, the sketch. So let us select the faces to partition. So these are the faces. Okay, so we'll have the done and select an edge. So I'll select basically this edge. Okay, so now we need to have a line drawn. So let us draw a line. So now let us keep it the length of the distance of this line at 50 mm from the center. So keep it as 50 mm. So our sketching is complete. So now let us do the partitioning along this line. So let us select the cells to partition. Now use the point and the normal. So should pass through this point. It should be normal to this edge. So create partition. So as you can see that yes, we have generated all the required partitions. Yes. So now we can proceed for the generation of the second part, that is basically the pin. So go to the create, so call it as the pin, and it's a 3D deformable solid extrusion. Everything remains the same. We'll keep the approximate size as 100 mm. Continue. And now let us first create the head. So draw a circle. Okay, we know that the diameter of the head is 40 mm, so the radius is 20 mm. So 20 mm. Now let us proceed for extruding the head. And we know that the head thickness is 15 mm. Okay, so means our one head is over. And the next, let us proceed for creating the shank. So we shall select the plane and one edge. Okay, we know that the shank radius is 12 mm, that's diameter is 24 mm. So the sketching is over. So let us proceed for extruding the shank. Now we know that the thickness of the length of the shank will be 3 times the thickness of the plane, because it has to accommodate all the 3 lugs. So this means that the depth should be 3 into 16, 48 mm. So 48. Okay. So yes. So now we need to create one more component of this part pin, that is a second head portion. So proceed in the same way. So let us select this edge and we'll select this edge also. Okay, so the procedure will be exactly the same. So let us draw the circle. and keep its radius as 20 mm. Okay, so that's okay for us. So now we are ready to do the extrusion from this. So the thickness will be 15 mm. So 15 mm. Okay. Okay, so our second part for the pin is complete. Now let us divide this pin into 4 equal parts exactly through the process of a partition. So let us go for the XY plane. So first of all, let us create the two lines. So we can use the face and the sketch. So select the face to partition, this one, and done, and proceed for the right edge. Okay, so now let us draw the two lines that represents the lines through which our partitions should pass through. Okay, that's a horizontal line. Similarly, create a vertical line also. Okay, so my sketching is complete. Done. Now it's a matter of just creating the partition planes corresponding to these two lines. So go for partitioning and select cells to find the cutting plane. You should use the point and the normal. So let us first create the horizontal plane. So should pass through this point and should be numbered to this line. So as you can see that yes. So we have done the partitioning along the horizontal diameter. Now similarly, let us proceed for partitioning it along this line. So first of all, select the cells. Done. And select this point. It should pass through this point and it should be numbered to this edge. Create partition. So this means our partition is now complete. As you can see that yes, this entire pin, it is divided into 4 parts, 1, 2, 3, 4. Okay, so remember that our purpose must be to partition the any component, any part into simple parts, because that will help us in doing the meshing using the proper shapes and with the proper aspect ratio. So this means that the second part, that's the part pin, is complete. Now we can proceed for the next module, that's a property. Here, as already explained, we have two materials. So let us proceed for creating first the steel. This is the material for our pin. So the steel. Okay, so mechanical. So go for the elastic part. So we will be using 2.1 into e raised to 5 MPa, and my percentage will be 0.3. And remember, we'll be using Newton and millimeters consistently all throughout our tutorial. So now let us proceed for the plastic component. Plastic. So the yield stress for the steel, it will be 355, and the corresponding plastic strain will be 0. And the ultimate stress, this is our bolt. So bolt means our the yield stress will be 640 and the ultimate stress will be 800. And the corresponding plastic strain, let me keep it as only 8% because of bolt material. So means that the definition of the steel material that is required for the pin part, it is complete. Okay, now let us proceed for defining another material, that's aluminium, and this aluminium will be used for all the 3 lugs. So call it as aluminium. Okay, so good mechanical, provide its elastic properties. The Young's modulus will be 7E4 MPa, and the Poisson's ratio will give it as 0.3. And then we'll go for the plastic properties, plastic, and the yield stress. We'll keep the yield stress as 125 MPa, and the corresponding plastic strain as a 0. And then the ultimate will give it as 250, and the associated plastic plastic strain, we'll keep it as 0.15. So that's okay. So means we have defined the two materials. Now let us proceed for creating the sections. So let's first say section for say the pin, section for the pin. So let's continue, and we know that the pin will be the material will be the steel, and so this is okay. And let us create another section that is for our lug, okay. And this lug, we know that it is made up of aluminum, okay. Now we shall start assigning these sections to the various parts. First go to the lug, okay, and then assign the section. So let us select the entire lug. So this is my lug, done. And here this is be my section lug, okay. Now you can see that the color has turned green, indicating that yes, the proper material has been assigned to it. Now similarly, let us go to the other part. There's a pin, and assign the sections. Select the regions as usual. So done, and we shall select the section pin. Okay, okay, fine. So this means that the section as well as the property assignment is complete for both the parts. That's for the lug as well as for the bolt. Now this means that we are ready to proceed to the next module, that's assembly. Okay, so in the assembly, what we need to do, we need to rearrange all the parts in such a way that we arrive at the required component. So here we have the two parts. So let's first create the instance of the lug part. So this is okay for us. Okay. Now we shall create a second instance, because remember we have three lugs. So we have to create three instances and we have to properly place them. So let us create another instance, that is again another instance of the lug. Okay. So okay. So first of all, let us translate this instance to a proper distance. So translate. So select the instance, select it, done. So let us translate through along the z-axis. This is just for the convenience in handling this instance. Okay, fine. Now as you can see, so this is position is okay for me. Now first thing is that we want to ensure that this part, in this semicircular part, this comes on my left side, not on the right side. So let us first rotate this second instance about this vertical axis. So how do we do it? Very simple. Go to this rotate instance. Okay, so select the instance rotate. This is my instance rotate. Done. And now we have to select the start point and at the end point of the axis about which it has to be rotated. So I have selected, and the angle of rotation, this will be obviously 180 degrees. Okay, so you can say that yes, this position is acceptable to me. Okay, now we shall move this instance so that these two holes will be coaxial. So go to this coaxial constraint, and it will ask you to select the cylindrical surface of the mobile instance. Select it. It will ask you the cylindrical surface of the fixed instance. Select it. And now we know that the normals are in the opposite direction, so flip it. Okay, this is okay. So now you can see that yes, these two holes are coaxial, right? Now you also know that the distance between these two faces should be exactly equal to the lug thickness. So let us again use one more constraint known as the face-to-face constraint. Okay, so you last you select a part face of the mobile instance. There's a one face and there's another face, and the normals are in the same directions. Okay for me, and we know that the distance between these two faces should be 16 mm. Okay, yes. So we have now properly located the second lug with respect to the first leg. So as you can see, if you see for example, just rotate it a little bit, you can see that the two holes are exactly coaxial. You can just zoom it a little bit. Two holes are exactly coaxial and they are being properly placed in both x and y and z directions. So this means that the placing of the second lug component is complete. Now let us call for the third part. So create instance of for the third lug assembly. So this is okay. Now let me just like the other lug, let me just position it properly. So I'll translate it first. Translate the instance, select the instance first. It's okay. So I want to translate it along the z-axis by say 100 mm, 100 mm. Okay, that's okay for me. Now, as you can see that we need not to rotate this instance because we want this part to be on the right side only. So, but we have to shift it in such a way that the haulers are coaxial. So let us again a similar way apply for the coaxial constraint. So you'll ask you, this is my mobile cylindrical phase. This is for, and the two normals are in the opposite direction. So now flip it so that they are in the same direction. So this is okay. So as you can see that yes, now the third instance is placed in such a way that the three holes are coaxial. Now let us move this using the face-to-face constraint. So go for the face-to-face constraint. Now select the panel face of the datum plane of the mobile instance, this one, and this another one. Okay, and the normals are in the same directions. So it's acceptable to me, and this is 16 mm. Okay. So we find that yes, all the three legs are now properly placed. So you can just take it a little bit to the side. You can zoom it, just rotate it and see whether all the three holes are. Yes, you can see that all the three holes are now properly aligned. Okay, so this means that we are ready to call or we are ready to create the instance for the pin part. So create an instance. So keep it pin. Okay, so now let us first of all uh, move this around the z-axis so that we get a proper distance. So down, so we can done. Okay, and we'll replace it. So that is 100 mm is good enough, I think. Okay, good enough. So let us call it as it's okay. So let us shift this bolt so that it is coaxial with this. So how do? We proceed for the same coaxial constraint. So select the two faces, one, and this is the two. Okay, normals are in the same direction. This is okay for us. So you can see that yes, the bolt is translated such that it is coaxial with our three holes. And now we need to use again the face-to-face constraint. Okay, so what we can do is we can keep this face-to-face constraint applied once again, face-to-face constraint. Okay, so let us select the two faces. This is one face and this is another face. Normals are in the same direction. This is okay. And now the distance will be obviously is the header distance, the thickness 51. Yes. So now we find that yes, the bolt is also properly located. So you can also just rotate it and see the other side as well. Yes. So this means that we have created the assembly of this three of the two parts properly. So we can now proceed for the next module. That's a step module. So let us create a step first. So I'll call it as a step lug-pin. Lug-pin. Okay, and the analysis type that we will adopt is a static example. Continue. Okay, now go for this. Remember, we have provided to Abaqus all the nonlinear geometry, all nonlinear material properties also. So keep NL geom as on here, and also go for the automatic stabilization procedures because it's a contact problem. So we may arrive at some kind of a non-convergence issue. So always keep this automatic stabilization on with this option. Now go for the implementation. I'll keep this a little bit larger, and the initial I will ask Abaqus to start with a step of 0.01 and keeping a maximum of 0.05. Okay, and this I will keep a little bit less because there's a possibility of non-convergence. So I'll keep it as instead of 0.5 as 1 minus 5. So this is okay for me. It's okay. So now let us proceed for creating the field output variables. That means what are the variables to be returned to the output variable in Abaqus. So I'll call it as F output for my lug-pin assembly. Lug-pin assembly. So this for the step is okay. Continue. Now let us proceed for selecting the required outputs. So among the stresses, I'm interested in the stress components and then variance. Select it. Okay, and now I will proceed for the displacements. I'm interested in the U translations and rotations. Select it. And the contact problems. Obviously, I'm also interested in the contact stress. Select it. That's okay for me. And all these default parameters are acceptable to me. Okay. So this means that we have completed the step module for this tutorial. Now, regarding the balance modules, that's interaction, load, mesh, job, and the visualization will be taken up in the next part of this tutorial. That's a part B.